Hello and welcome. My name is Celeste, and today I'm going to enlighten you with some knowledge about circular polarization and circular polarized light. So get comfortable and ready to learn. When I started my undergrad research in the optics lab, I was very excited to work with lasers, mirrors, and polarizers, but I didn't understand well how it worked. So I wondered, what are polarizers? What do they do physically to light? Why would we use them so much? The truth is, we even use polarizers in regular cameras. If you like photography, then you must be familiar with this because polarizers are found in cameras to remove reflections, increase saturation, everything looks more colorful and pretty. They do this by polarizing the light entering, which causes some already polarized light to be reflected instead of passing through the filter and becoming part of your picture. So how does this work? Well, to get circularly polarized light, you first need, light. But to get light, and yeah, Carl, also to make an apple pie from scratch, first you need to invent the universe. So as far as we know, the universe is made of space, time, and some fields, and that's pretty much it. A field is just a value, it's just a way in which we assign value to every point in space. And kind of like the surface of the ocean, every point has a particular height given at a given time. And just like the ocean fields, the fields have waves that move through space and time. And one of these fields is the electromagnetic field. So what I'm saying is that every point in space and time has an electromagnetic value, but that value isn't just a number, it's actually a vector. It has a direction and a magnitude. Light is an electromagnetic wave, and it's a transverse wave, meaning that it oscillates in a direction which is perpendicular to the direction that it travels. Now, you might be thinking, what kind of universe is this? Where are the particles I studied so much in my intro physics classes? Where are the protons, the electrons, and the hamburgers that I'm used to see in the real world? And wait, isn't light actually made of photons? But honestly, if you made it this far in our course, then I don't need to explain to you that light sometimes behaves like a wave and sometimes like a particle. And yeah, it's coming back, right? The slit interference pattern. So, going back, in our many math classes, we have learned that there is this thing called vector addition, and since there can be positive and negative directions in the vectors, they can cancel each other, and you can end up with nothing. But okay, let's look at this diagram for a bit. So a wave has a phase, a wavelength, and a polarity. Here the polarity is the direction of the wave vector at any given point. And a laser beam looks kind of like this picture because it generally has one phase, one wavelength, but normal everyday light is really complicated. It has a whole bunch of polarities, wavelength, phases, all at the same time. And the wavelength of the light determines its color. So now that we have, so it's just, visible light is just an electromagnetic radiation within the visible range of 400 nanometers and 700 nanometers. And now that we have the universe and light and all this stuff, let me go back to my main point. So how does light become circularly polarized? And I'm sorry about that. And how do we use this circularly polarized light? So let's say how do we use them in cool physics experiments? Well, first, let's remember from our class that we need to consider the refractive index of the substance that light is going into, and also from where it comes from, which is basically how fast light travels through the material, and the law of refraction, described by Snell's law. So, to understand how retarders function, we need to consider the nature of the materials used in the construction. A material such as glass has an index of refraction which is the same in all directions of propagation through material. So these materials are called isotropic. But not all materials are isotropic. But there's a fancy and kind of expensive way to polarize light and how we want it. And by this, I mean polarizing filters. There are many types of polarizers, but we are going to talk about some specific ones that make light circularly polarized. And by those, I mean what I mentioned before, retarder or wave plates, specifically quarter wave plate. A wave plate resolves light into two orthogonal linear polarization components by producing a phase shift between them. And depending on the induced phase difference, the transmitted light may have a different type of polarization than the incident beam. Some common retarders are the quarter wave plate and the half wave plate. A quarter wave plate is used to convert linear polarization to circular polarization and vice versa. In order to obtain circular polarization, the amplitudes of the two E vectors components must be equal and their phase difference must be 90 or 270 degrees, yes or yes. So a quarter wave plate is capable of introducing this 90 degrees phase difference between two components, and however, this is not enough to produce the circular polarization we want. The direction of the polarization of the incident light with respect to the optic axis of the quarter wave plate is equally important. So to get the amplitude of the two components to be equal, the incident linear polarization direction must make an angle of 45 degrees with respect to the optic axis of the crystal. And as well as if circular polarized light is incident on a quarter wave plate, the resulting polarization will be linear at an angle of exactly 45 degrees with respect of the optic axis. Again, the reason is what we just mentioned. That is that the phase difference of 90 degrees is introduced between the two components of the electric field vector, and which traces the helix-like path that the circular polarized light propagates. But now let's express this mathematically. Let's consider the totally linearly polarized light that emerged from a linear polarizer. And if a quarter wave plate is placed between the first polarizer and the second polarizer, the transmission function can be derived as follows. In figure A, here, the x-axis is along the transmission axis of the first polarizer, and the x-prime axis is along the optical axis of the quarter wave plate. The angle between the x-axis and the x-prime axis is alpha, and the electric field vector along the x-axis, which has an amplitude of E0, can be decomposed into two orthogonal components along the x and y axis. The quarter wave plate retarder shifts the phase of the component along the x-prime axis, along the x-prime by pi over 2 radians. And notice that the magnitude of the electric field vector that results after the quarter wave plate is still zero. And therefore, the transmission function of the quarter wave plates is just I equal I naught, where I is the intensity after the quarter wave plate, and the I naught is the incident intensity. And You can see in figure B that the components along the x prime and the y prime axis are projected into the x-axis, x double prime axis, which represents the transmission axis of the second polarizer. And the x double prime axis makes an angle beta with the x-axis, or an angle beta minus alpha with the x prime axis. And the resulting E field is our equation shown in here. This simplification of this yields to the intensity I of the transmitted light to be proportional to this last equation here. And this direct relation with the intensity let us consider these very practical instruments for use in many types of optical setups. Even in some recent experiments, it has been shown how to directly transfer orbital angular momentum from photons to atoms and vice versa. While we understand how linear momentum and spin and angular momentum transfer from light to atoms, the action of the orbital angular momentum is less obvious, and the transfer of linear momentum is linked to radiation pressure and the scattering force. The spin angular momentum can be transferred from circularly polarized light to the atom by driving transitions between different atomic spin states. But this is beyond the scope of my presentation now, but there are some very interesting topics and a lot of ongoing research going on right now, and the application of circularly polarized light is very important. So I hope you enjoy. Thanks for watching, and I hope you learned something. And if you want to know more, then I'll leave the resources below. Thank you. Bye.